Hi, welcome. We're still continuing with 4.2. Remember, we're still doing a revision from this paper. This is the paper, control test 1 2022 from it's a provincial paper, Limpopo. So yeah, so check out other videos. We've done all of these questions. I've done question 1 and 2 and 3, and we've done question 4. This was question 3. There's my question 4. We've done question 4, 4.1, and now we're doing question 4.2. Okay. And then for the next video we'll start question 5, and this is how question 5 look like. So tune in. We're about to be done with this paper. 4.2. In the figure below, we have E. E is the center of the circle. So they tell you that E is the center of the circle. That's E. E is the center of the circle. Okay. And DE is perpendicular to AB. So where's DE? This is D. This is E. So it's perpendicular. So therefore this is 90 degrees as well, because perpendicular. So let's write that down. So we are being told that DE is perpendicular to AB. So DE is perpendicular to AB. Therefore, that means this is both this angle and this angle are 90 degrees. And then they tell us AC. This is AC, and DE. Where's DE? This is DE intersected F. Okay, they meet here. That makes sense. And DF and DC are equal. Okay, so DF, this is DF and DC are equal. So let's write that down. DC and DF are equal. Right. Now 4.2.1, prove that BEFC. So where's BEFC? BEFC is a cycle quadrilateral. So prove that BEFC is a cyclic or cycle quadrilateral. So how do you do that? So basically, let's just write triangle. I mean, not a triangle, a circle around this. So let's make it actually bigger. Make it a circle. Okay, so to prove that something is a quadrilateral, so a circle is or maybe a figure in this case, which is a polygon. We call these things polygon. Prove that now this polygon is a cyclical quadrilateral. The way to do it is you need to prove. You can prove it in 3 ways, really. You need to prove that the opposite angles, if you add opposite angles, they give you 180 degrees. So the opposite angles are supplementary. Even this one, if the opposite angles, if you add them, give you 180 degrees. Therefore, this figure here, is a cyclical quadrilateral figure, which is a cyclic. It's hard for me to say this word. I don't know why it's so hard. A cyclic quadrilateral is a polygon, right? This polygon is a cyclic quadrilateral. Okay, so you can either show this if you add them to 180 degrees, or this is equal to 180 degrees. Or another thing is, so if you have, because this is a straight line, so this and this should be equal to 180 degrees, right? So the angle, the exterior angle is equal to opposite interior angle of a cyclic quad. So a cyclic quad, this is a cyclic quad if this and this are true. Those are the 3 ways of doing it, right? So you can now look around and see what you have been given. So firstly, we know this for sure, this is 90 degrees. So if this is 90 degrees, and if you can prove this is 90 degrees, therefore if you add these two, they should give you 180 degrees. So that's one way to do it. You can look at other ways as well, but I mean that's the obvious one, because we're already being told this is 90 degrees, so you can write that down. So CE2, you can write that down. E2, angle E2 is equal to 90 degrees. Why? We're already being told that DE is perpendicular to AB. We are being told that. That's the reason. Okay. And then now we need to prove that C1 is also 90 degrees. So if you add these two, they should give you 180 degrees. Therefore, if they're supplementary, boom, it's a cyclic quad. Right. Okay, let's how do we do this? If you just look at this alone, right? This is a diameter, and then this is an angle. Now, if you remember, it's just quick revision. If you have, let me just take a different color. If you have a circle, okay, you have a circle and you have a diameter. This is being told is a diameter. So this angle here is equal to 90 degrees. There's a theorem that says if you have a diameter and then that angle over there is equal to 90 degrees, right? Just the reason behind it, the angle in a semicircle is 90 degrees. Angle in a semicircle is 90 degrees. So this is the same thing. This is a diameter, and then you have this angle here. C1 is an angle that is in this, it's an angle from the semicircle, right? Or an angle from a semicircle is 90 degrees. An angle from a semicircle is 90 degrees. So you can just write that down. So you can say then angle C1 is equal to 90 degrees. Why? The angle, it's because it's an angle in a semicircle. It's an angle in a semicircle, right? Or you can simply say because AB is a diameter, right? AB is a diameter. Because AB is a diameter, if AB is a diameter, therefore C1 is an angle, and it's an angle, that same angle is 90 degrees, right? And then C1 is equal to 90 degrees. So now these two, so if you add angle 2 plus angle C1, they give you 180 degrees. Therefore, angle C1 and angle C2 are supplementary angles. This tells us that BEFC is a cyclic quad. Boom. That's how you do it. So let's revise. What we did is we were told that this and this are perpendicular. So we are told this is 90 degrees. So if this is 90 degrees, therefore this is perpendicular. So this is E2 is 90 degrees. So if E2 is 90 degrees, why not just then figure out what is C1? Of course, our hypothesis is C1 should be 90 degrees. Now we look at, oh shit. So we know that AB is a diameter. So since AB is a diameter, therefore C1 is 90 degrees. Therefore this and this, if you add these two angles, they give you 180 degrees. And by definition, we know that if opposite angles are supplementary, therefore that is a cyclic quad. If opposite angles are supplementary, therefore that is an acyclic quad. And lastly, if you know this and this are equal, therefore is a cyclic quad. By the way, the converse is true as well. 4.2.2. Prove that DC is a tangent at C. So where's DC? DC, this is DC. So prove that DC is a tangent at C. So what's happening is now we're looking at, so this is DC. They want to prove that DC is a tangent of this bigger circle, right? Prove that DC is a tangent of this bigger circle. Prove that DC is a tangent of the bigger circle. Okay, let me give you a theorem, a revision of a theorem. So let's say you have a circle, and then you have tangent, right? Now there is a theorem. Let's just take it down, because a tangent is a line that touches the circle once. That's a tangent. That's a definition of a tangent. Tangent is a line that touches a circle once. So there is if you have a tangent in the circle, and then you have this polygon here within a circle. Boom, 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 boom. Okay. By the way, it touches. Okay, the trick one. It touches all the points. So with the point here, with the point there, and have a point there. So now this theorem says that an exterior angle is equal to what's this theorem says? It's not an exterior angle, but it says an angle between a tangent and a chord is equal to this angle here. An angle between a tangent and a chord is equal to that angle here. Okay, so if we can prove that this is equal to this, therefore we know this is a tangent. Also, if you can prove that this is equal to that, therefore this is a tangent. All right, so an angle between the tangent and the chord, because remember this is a tangent, and the chord, this angle is equal to this opposite interior angle. An angle between a tangent, this is a tangent, and the chord is equal to the opposite interior angle. So that's what we're going to be doing here. So if you look at this, right, if you look at this, I don't want to do this because we're going to use this information later. But if you look at, look at this, boom, right? And then this is a tangent, right? So if this is a tangent, so if we can prove that C2, this is an angle between a tangent and a chord, right? An angle between a tangent and a chord is equal to this angle, which is an opposite interior angle. Therefore, we've proven that this is a tangent. Okay, that's what you need to do. So prove that C2 is equal to B. Okay, how do we do that? Firstly, we need to see C2. We need to see that C2 is equal to F3. C2 is equal to F3, right? Why C2 is equal to F3 is because of this. So there isn't a theorem. Just another revision. Just quick revision. So there is, if you have a triangle like this and you are being told that these opposite sides are equal, therefore you should always know that the base angles are also equal. Opposite angles are also equal. If opposite sides are equal, therefore the base angles are equal. That is a theorem that you have learned in grade 10, 11, and 12, even in grade 8. So the base angles, if also the inverse is true, if the base angles are equal, therefore the opposite sides are equal. If the opposite sides are equal, therefore the base angles are equal. I can keep saying that just to be in your memory. So now we have this triangle as well. This is a triangle. Opposite sides are equal, therefore base angles are equal. So we can now just write that down and say angle C2 is equal to angle F3. Is it 3? Yes, angle F3. Why? Because we know that DC is equal to DF. We know that DC is equal to DF. That's the reason. Or you can write this reason if you want to. You can just say opposites. Okay, you can say we can just say probably angles of opposite equal side are also equal. Okay, angles of opposite equal sides are equal. Angles of an opposite equal sides are equal. Depending on how you wanna, what reason you wanna write. Okay, and then so you get that C2 and F3. We find that now they are equal. That's what we know. So this, let me write a different color. This and this are equal. Okay. This and this are equal. And then by the way, if you remember, I said if to prove that this is a cyclic quad, you need to prove that this exterior angle is equal to this interior angle. But now we already know that this is a cyclic quad. Therefore, by that definition, this is equal to that, right? So angle B is equal to angle F3 because we've proven that BEFC is a cyclic quad, right? So we can just write that down. Easy, right? So F3 is equal to angle B. Why? Because BEFC is a cyclic quad. Now, if C3 is equal to F3 and F3 is equal to B, therefore angle C2 is equal to angle of B. If angle C2 is equal to angle F3 and angle F3 is equal to angle of B, therefore angle C2 is equal to angle B. That's what we wanted to prove, right? We wanted to prove that angle C2 is equal to angle B. So if these two are equal from this definition, therefore this is a tangent of this bigger angle. Okay, so this implies that, okay, therefore this implies that DC is a tangent at C. What's your reason? Because of a tan chord theorem, right? If you don't know a tan chord theorem, please go back into my previous video on 4.1. I proved to you a tan chord theorem. This is what we did. You can also just pause this question and just look through it and see how we prove it. But otherwise, this is the application of a tan chord theorem. The tan chord theorem says if this angle is equal to that angle, therefore this is a tangent. Yeah, well, so if you have this is equal to that, therefore there's a tangent. If you have this is equal to that, therefore it's a tangent. Tan chord theorem. Tan chord theorem it talks about an angle that is between a tangent and a chord, and that angle is equal to opposite interior angle. Boom. So this is how you would do 4.2, and then you get your marks. Just 3 marks. 1, 2, 3. Boom. And you get your 1, 2, 3. Boom. Right. So this is how you get your marks. And now see you to the next video on question 5. We'll be doing all of this questions, and this will be our last video for this paper. See you there. Awesome.